Hi guys, in this video on solving quadratics, we're going to talk about quadratic word problems. This is part one of two parts. I split this up into two parts because, for starters, the quadratic formula is difficult for many students. Second, this video would have been very long if I didn't break it up into two parts, and I think that would have been a lot to ask of anybody watching this video on math. So let's get started. Most quadratic formula word problems at the high school level involve projectile motion. And the reason for that is it's relatively simple to track the motion of an object over time, specifically track the height. So what we're going to be doing here is we're going to be creating models of an object in reference to height and time, if that makes sense. So we're not going to be focusing on forward motion or how far an object went for the most part. What we're going to be focusing on is how high and how long it took an object to get there. Doing so, for the most part, we can ignore things like aerodynamic drag and other climate conditions in which the object was thrown and get a relatively accurate result. I created this graphic organizer a little while back, and it kind of maps out what you want to do for what you're looking for. So example, if you want the initial height, you can just look for C of the quadratic equation that was provided. If you want to know how long it took the object to land, you can solve using the quadratic equation. Moving up, that's the one that kind of scares students, but it's actually not as complicated as it sounds. Essentially, you're setting the quadratic equation equal to an indicated height. Then you're setting it equal to 0 anyway, which is something that's pretty standard procedure. From there, the tricky part for this video will be finding the highest point. That's typically used different equation. So we have two methods for finding the highest point. One of them is to use the axis of symmetry equation, which I will show you in this video. The other way, which is the way I teach my students, is to just follow through on the quadratic formula, then divide those results by 2. From there, you could take that answer and then plug it in for time, and that will allow you to get the highest distance it traveled. All right, let's take a look at an example. Okay, let's take a look at an example here. We're going to throw a ball. So to find the initial height, I select C. So the initial height here is 3. Then the height when the object lands is 0. And the height at the indicated line here will be 20 on both of these. Alright, now what I need to do is figure out my height at launch, which will be 0. Then I need to figure out how long it took to land. Well, in order to do that, I'm going to have to use the quadratic formula. So, if you need to watch how to perform the quadratic formula, you could watch my previous video, or what you could do is you can... Okay, so we're going to start by plugging into the quadratic formula. Forgive my handwriting. My pen that usually works with the Surface stopped working for some reason. But we're going to carry on here. No broken electronics going to stop us from mathing this evening. And I'm going to just plug into the quadratic formula. And I'm going to try my very best to draw straight lines with this odd delay that this tablet is creating. There we go. All right, now that I managed to get through that, I guess my answer to how to perform the quadratic formula in this case is that you need a really, really good calculator. So I am relying heavily on a calculator to solve this problem. I could not do it otherwise. Good calculators are 20 bucks. I've gone on plenty of rants throughout my videos on this. I am currently using the TI 36X Pro to get this problem done. Okay, so what I did is I plugged the stuff under the root, which is called the discriminant, into the calculator to get this answer, 1792. With the calculator that I have, I was able to plug that in exactly as I see it. Now what I'm going to do is I'm going to plug this 40, which that should be a negative in the front there, fixed, into the calculator. The way my calculator has a fraction button, so I can just use that and plug it in exactly as I see it. The way I'm plugging into the calculator is first I am doing the positive or the plus part of the equation, which would give me negative 0.07. Then I'm going to plug in the negative part, and my calculator here just allows me to reselect the original fraction that I punched in, or this original thing I punched into the calculator, and just change that negative to that positive to a negative. So these are my answers. We generally ignore this negative 0.07, and the reason for it isn't because it doesn't exist as a quadratic function. It's because it doesn't exist physically in this case. And the reason for that is that negative 0.07 is the first x-intercept that happened prior to launch. So in other words, this part of the graph does not exist. But the 2.57 does. So I'm going to plug that in, and that is 2.57 seconds the quadratic formula gave me. Alright, now let's see how long it took to get to 20 feet high. Okay, what I need to do is I need to plug in 20 for h. So I'm going to rewrite this equation with the equation set equal to 20. And from there, what I'm going to have to do is I'm going to have to set it equal to 0. And that's standard procedure for a quadratic equation, because they cannot be solved unless the y part of the equation equals 0. And as mentioned before, the reason that is because you're trying to find the x-intercepts. That is what's considered the solutions for every equation, pretty much. It's the reason why we use x as a variable so often. So now, in this particular case, c has changed from 3 to negative 17. So I'm really doing the same procedure again, but I'm putting in negative 17 there. Okay, let's see what I get. Okay, when I plugged the discriminant into my calculator, I got 512. Again, if you're really clever with how to use a calculator and you have a good one, you could just hit the up button, select the original discriminant you plugged in, and then from there just change C. This isn't a practice of fighting through the quadratic formula. You should have done that already. This is a practice of learning what the quadratic formula does and how to read the results. So now let's see what the times are for 20 feet. Okay, so for the positive side of the quadratic formula, I got 0.54 seconds. Now I'm going to punch in the negative side, and I'm going to get 1.95 seconds. So I'm going to fill that in. All right, we got one more thing to do here, and that is to find its highest point. So let's work on that. There are two ways to find the vertex or the highest point, in this case, of a quadratic function. And the way I typically teach my students is to take the results of the quadratic function and then add them together and divide by 2. The reason why I do that is because the class I teach, the students need a lot of practice with the quadratic formula for their future math class. The Georgia curriculum eventually focuses pretty heavily on the quadratic formula, so I just want them to get that practice. So let's take a look at the other method. Okay, the other method finds the x value for the axis of symmetry, which is, in most quadratics, an x line. So x equals some kind of line here. And the formula for that is negative b divided by 2a. So I could once again plug in to these letters and get the answer. Negative b over 2a is just part of the quadratic formula. And somebody, probably a very, very long time ago, figured out that if they use that part, they can get that axis of symmetry. Either way will work. So it's up to you. Frankly, it also depends on what the question's asking for, because when it asks when an object is going to get to its highest point, you could avoid the quadratic formula and just use the axis of symmetry. Okay, let's plug that. Now what I need to do is, to get the height, I need to plug that 1.25 into the time of my quadratic function. So remember, quadratics are a function. So that means when you add an input, which in this case is time, you will get an output. And in doing so, I will be able to get the maximum height of my ball. Let's see what the calculator has to say. So my calculator says that my object went 28 feet high. Okay, couple of things we want to talk about. So let's take a look at what we found. So for starters, let's talk about that negative 16 in the front of this quadratic formula. That is Earth's gravity. So this object is being thrown on the Earth. Every planet has its own coefficient, and you could actually look them up, and it's amazingly interesting. 40 is the amplitude at which the object was thrown. My guess is it would be in foot-pounds or something like that. Then 3, in this case feet, is the initial height. So that's the way that reads. Now, what has happened is the object has started at 3 feet high, was thrown into the air, and it took half a second for it to reach 20 feet. Then it reached a maximum of 28 feet at 1.25 seconds, or 1.25 seconds, but then gravity won the fight and it started to fall back down and hit 20 feet again, or past 20 feet again, at 2 seconds. From there, it landed in 2.5 seconds after it launched. So using the quadratic formula, we were able to model the path of this particular ball that was thrown. Now, mind you, the problem does not provide context of how it was thrown, where it was thrown, if it was thrown in a vacuum or if it was thrown in the field. We don't know that, and knowing those things can potentially make this problem more complicated, which is outside the scope of the basic math that we're learning here. Okay, guys, I hope you found this video helpful.